So I will talk about although the classes is nanoscience and technology, but I will talk mostly about these materials and their applications. Okay. So if you see, there is always a demand on materials. What is this demand? Always people want the high efficiency of the materials, efficiency in terms of various factors. But at the same time, people want a materials with a cheaper price. So there is always a tug of war between the higher stress level of a material, higher pressure of the materials, higher temperature application, higher speeds, more severe environment, higher functional properties, and at the same time, we require the cheaper material, stronger material, material should be of smaller cross section, the component should be of miniature size, and the life is also very much extended. So there is always the tug of war between these two in the development of materials. So this actually motivates the scientists and engineers to develop newer materials and processes. What are the materials? Any physical matter that is used by man to make things required by him is the materials. But in terms of engineering materials, we can divide it into various categories. One is the metals and alloys. One is the semiconductors like gallium arsenide, indium phosphide. Like glasses, borosilicate glasses, soda, silica, polyester or polymers, like polyester, polycarbonates, biomaterials, hydroxyapatite, ferrofluids, like that, and ceramics, that alumina, silicon nitride, zirconia, high temperature superconductors. So these are different categories of materials. Besides this, there is another category of material which is called composite, which is the combination of one or more area together which can make a composites. So the engineering materials, when we're talking about the engineering materials, we'll talk of the metals and alloys. This may be ferrous alloys or non-ferrous alloys. We can talk about the semiconductor materials. We can talk about the glasses. We can talk about the polymers. We can talk about the biomaterials. We can call the ceramics and also the composites. And you see, with the evaluation of scientific discovery, how we can get the materials and with higher strength. So initially in around 1600 years, 1700 years, we have the cast iron, then the steel, then the aluminium, then the composites, then the carbon fibers. And you can see, particularly for last two centuries, we have really a dramatic change in strength of the materials with the advent of various types of newer materials like carbon fiber, composites, aluminium, different types of aluminium. So this leads to, you see, a evolution of aerospace materials also. You can understand, we started with just a balloon, then there is a combinations of wood and metals and fabrics. Then we have a materials which can go to 200 degree Fahrenheit, then 800 degree, and then This was possible because of the invent of various materials which led to the development of different engines, high temperature engines. Even, and not only the development high temperature engines, their size is also getting reduced. So this is basically evaluation of operating temperature in aerospace engines, and with those development of materials, the aero industries is changing from the balloon to a supersonic jets. So materials plays a major role in our
Hello, sir.
security. Yes,
Sir, presentation is not visible for me.
is not visible.
So it
Yes,
is
sir.
visible.
For
It is visible for me.
So you should have told earlier.
yes, sir.
It is visible.
Maybe network problem.
Okay. Okay. How we can? I can stop it and again we can start. Okay. Is it now visible?
Yes, sir.
Yes, sir.
So again, then I'm starting from the beginning, but faster. So there is always a competition between the higher efficiency materials and how we can reduce the cost, which lead the demand of the materials. And there is a tug of war of getting the high stress level materials, high pressure materials, high temperature materials, materials for high speed application, more severe environmental applications, and higher functional material properties. At the same time, we require the cheaper materials, stronger materials, lower cross sections, miniature size, extended life of the materials. So this leads this competition between the higher efficiency and higher type of materials, that is we can get the cheaper, stronger, lower cross section, particularly the miniaturized size and the extended life of the components. This too is the motivating factor for the scientists and engineers for development of newer materials and processes. And if you think the materials, each can be divided into different categories, that is the metals alloys. You can see now, you are able to see it now. Are
Yes,
you
sir.
able to see the slides?
Yes, sir.
Yes, sir.
So metals and alloys, semiconductors, glasses, polymers, biomaterials, ceramics, and a combination of these, which is called the composite materials. And this shows in the last centuries, there is a tremendous newer materials which lead to the strength of the materials with the weight density. What it means, the strength of the materials is higher with the minimum, and the material is become lighter and lighter. You see, it is the strength of the material or density. So cast iron, steel, and then aluminum is much lighter than the composite and the carbon fibers. So this type of development of materials lead to the evaluation of various applications. One such application is the aerospace industries, which started with the balloon and with the different materials, titanium alloy, aluminum alloy, ceramics, super alloys, and composites. It leads to a materials systems which can withstand a temperature of around 3000 Fahrenheit. This was possible mainly because of the development of various aero engines from 500 degree Fahrenheit, started with the 500 Fahrenheit to 3500 degree Fahrenheit. And this also, the engine size was also reduced with the use of various high performance materials. So when we talk what wish to develop materials, synthesis is one of the factors. And when we have to do the synthesis, we have to do the three areas in mind. One is the what is the properties of the materials, what is the structure of the materials, and not only that, what is the performance of the materials. Now, the materials which with the poor performance doesn't have anything. So when we synthesize the materials, we have to always keeping in mind the properties, structures, and the performance so that this material can be utilized for applications. And whenever I am talking about the applications, we have to always think the materials application for having a commercial value of it. So, there is the need to selection of materials for structural applications. If you consider for the structural applications, these are the three properties: the strength, toughness, and hardness. These are the very important properties of the materials. And not only with that, we have to also think various factors with that. That is the how it can formability, how we can give a particular shape of the material, how we can join the material, how the material have a corrosion resistance, and definitely the affordability. And if we think the metal has almost all the criteria, but if you consider ceramics, its formability is poor, but the strength is high, and resistance to corrosion is quite high. And the composite, that's why the composite has come, which has a moderate formability, affordability is also moderate, strength is high, and it has also the joinability. So we have to consider all these factors whenever we are going to develop a newer materials. So what is the strength of the materials? The strength of the materials is measured from the stress versus strain curve. You have to put these materials in the two jaws and try to pull it. And when you pull it, you are giving some stress, and the material, some strain will generate in the material. So we all know about the, we have studied that Young's modulus, that the stress versus strain curve. But if we go for the stress versus strain curve up to the breaking point of these materials, then we can get a curve like this. So the parameter by which strength of the material is determined is called the yield stress. So if we go for the stress by strain curve, we can see that it is a linearly increases, then there is a kink, and then again there is an increase and fall down, and breaks, material breaks. So when this kink is observed, that is called yield point, and the stress corresponding to the yield point is called the yield stress. Many of the times you will not find this one. So in that case, you see particularly this case, you cannot find this one. So in that case, what is the strain value at point 2? You have to go parallel to this one, and where is cut with the stress strain curve, that is my yield stress. So, if we get a curve like that, there is a kink, then it is very easy to make the what is the yield stress. But in this case, we have to calculate with the 0.2% plastic deformation. This is called the plastic strain of the material. What is the toughness? Toughness is the ability of a material to
Hello, sir.
Yes.
Sir, the strain is controlled by experimental skills. It is possible or not?
Yes, can you say one thing one time more?
Sir, is the strain is possible is controlled by the experiments?
Yes, strain. There are two things are possible through experiment. The experiment is called the stress controlled, and also it can be called the strain controlled. Now the modern machine can do both the things, the stress controlled and also strain controlled. Okay. I have not told another parameters which is defined, that is called ultimate strength. This is the strength. If you go on increasing, many of the times you will get a maximum and then it fall down. Or many of the time you will find that it goes there and breaks. So this is this maximum strength the material can withstand. After that it will fall down. So there are two parameters by which a material can be identified. That is the ultimate strength or ultimate tensile strength. It is called UTS, and the yield strength, that is at this point. Basically, people are defined as the yield strength as the strength of the materials. Okay. Your question is clear? The answer is clear?
Sir, my question is that in theoretical study, we give the strain like 2% strain to a material biaxial. Then, how is it possible by experiments?
Experiment will do stress versus strain curve. It will do like that, a curve like that. Then you can measure this is the 0.2%, because suppose this is failed here. That is the 100% strain. So it failed here, not 100% strain. It failed here. So we calculate what is the strain value. That is considered as in 100% strain. And then you come down here and find out what is the 0.2%. Okay.
Okay, sir. Thank you.
So toughness is the ability of a material to resist breaking when the force is applied. When we force are applied, then how it can resist uh, the breaking of that material. It is basically the combination of strength and the ductility of the material. The material can be uh, ductile and material can be brittle. So it is the combination of the strength and the ductility of the material that is giving you the toughness. How it is measured? It is measured basically by the area of the stress curve. This is the area of the stress strain curve, and its unit is joules per cubic meter. So more this toughness is better this material for structural application. So we told you another parameters, which is the hardness. You see, hardness, it cannot be measured directly. Hardness is how well the material hold together when friction is applied. Common hardness substance include the diamond, drill bits, grinding disc, etc. There are two methods of hardness measurement. One is called the indentation. What is called? There is a sharp teeth here, and you have to place your material here. Now, you have to give a particularly load on this one, on the material, by which what is happen, a triangular, a rectangular shape or a square shape of will obtain, and you can measure the diagonal of this one, and this diagonal at this particular stress is the measure of the hardness. This is called the Vickers hardness, and so it is called something 20 Vickers hardness, or it is also called 20 Rockwell hardness. So it is the standard by which you are measuring with the standard tip, and by which it is defined as the material hardness. Not like here where we can use the joules per cubic meter, but when we are talking about the hardness, we are talking about what hardness you measured, Vickers hardness or Rockwell hardness. Is the Vickers hardness, so you have to tell is the Vickers hardness or Rockwell hardness and a value, 20 Vickers hardness, something like that. There is another method which is also the scratch hardness. This is basically required for the coating. In the case of the coating, how you measure the hardness, you cannot make a depth on it because coating is a very thin layer. So you can have a scratch on it, and through this scratch, you can determine and scratch hardness defines the resistance of the material to drawing. When we are doing the scratch, what is the resistance we are getting? That is called the scratch hardness. And again, it is also in terms of some unit, which is called Mohs scale. Diamond is 10 in that scale. So, as a combination of indentation comes sliding by a hard styler. That is the styler, and by which you will just pull on the surface, so it will make the scratch, and from there we can measure what is the hardness of this value. And you see, for the different materials, if we consider toughness, hardness is very high, then the toughness is small. So this is basically inversely proportional. So there is the motivation for the material scientist to get something which is a moderate hardness and good fractures of good toughness. So this also found that if we plot the strength of the material versus toughness, the curve is like that. But if we go for the material which is a fine grain, this curve shifts towards the right hand side. So finer grain structure, it goes towards the right hand side. And if we go like that, you can see with the same strength, same material, same strength, but we can get high toughness. So this is also a motivation to the scientist how we can go to the finer grain in a structural materials, finer grains towards the nano size grain, so that we can get strength but very high toughness. So this is a objective of the material scientists working on the structural materials, how we can get a fine grain structures or the nano-sized structure, or in other words, we can call it nano-structured materials, so that we can get a moderate strength but very high toughness. So this is the motivation for the structural materials group to go for nanostructured materials. So if you see the synthesis of the nanostructured materials, there are two approaches. One is the top-down approach, that is the bulk materials, and then go for disintegrate the materials into pieces or the fine grain, and which ultimately lead to a nanomaterials. Or in other words, which is called the bottom up, you started with atoms, then the clusters, and which lead to a nanomaterials. So we have two approaches. One is the top-down approach, one is the bottom-up approach. The top-down technique is starting material is mostly the solid state, and the bottom-up approach, the starting material is either gaseous state or the liquid state of matters. This is the in general. So the physical process by which we can go to the nanostructured materials through the top down is different physical processes. One of them is called severe plastic deformation. And severe plastic deformation has also several methodology. One is equal channel pressing, high pressure torsion, accumulated roll bonding, and other mechanical methods also cutting, etching, grinding, ball milling. There is also lithographic technique, that is by photolithography, electron beam lithography. There is also by rapid solidification of molten alloy, which is called melt spinning, copper mold castings. In the bottom-up approach, we have the physical and chemical process method. Both are physical and chemical. The physical technique is the physical vapor deposition, involves condensation of vapor phase species, evaporation, thermal or E-beam sputtering, plasma arcing, laser ablation. Chemical methods also, that is the chemical vapor deposition, involve deposition of vapor phase reaction species, plasma enhanced vapor deposition, CVD, or the self-assembled monolayers, electrodeposition, solvent method, microemulsions route, and pyrolysis. Okay, you can follow. You are following it, no?
Yes, sir.
Anything?
Yes, sir.
And any questions out of it, or it is okay for you?
It's okay.
Okay.
Sir, I need to ask about one thing. Graphene is also a nanostructure, and we build it from the top-down approach to the exfoliation, right?
Yes.
So, exfoliation is applicable for all other nanoparticles or not? Means we can get the other nanostructure of the other materials through exfoliation.
But in other structure may not be possible because of the spatial structure of the graphene. It has a two-dimensional structures. But if you want to do it for the others, that may not be possible.
Okay, and means if we are to want to make the nanostructure of other material, we can take any semiconductor material. Then
Yes.
we can't make it through the exfoliation.
I don't think we can do it through exfoliation. Durga, can you comment on it?
Yes. So I think in graphene, what is special is so like you make it from graphite, and graphite has a like
Two-dimensional
layered structure.
layered
It has
structures.
van der Waals interaction along the, say, if you talk about the z-axis, and in the plane it is a covalent bonding. So carbon-carbon bond is covalent, so that is much stronger. But along the z direction, it is a van der Waals interaction. So it is easy to peel it up. So you can make a 2D layer, and in the third direction, it's a very weak bonding. So if the material has such properties, such layered properties, then you can exfoliate and prepare these 2D materials. So therefore, all materials, you cannot prepare nanostructures, 2D materials out of all materials. So you cannot take iron and do that, or any typical metal, you cannot do that. So only special, so some of the semiconducting materials, like there is tungsten selenide, okay, or so some perovskite materials which are layered structures. So those you can do only. Okay.
Durga, is there any attempt to do this perovskite structure by exfoliation?
With exfoliation, actually the problem with exfoliation is you are not always, you cannot control
Okay.
the size and the, like how large it is. So it does not have, I mean, for like
Yes, sir, but
some research or investigation, it is good. But if you really want to go for devices, a large scale manufacturing, exfoliation is not really going to work.
No, exfoliation is not going to work.
okay. So, sir, which one is the most preferred method in this top-down approach if we will follow for other parasite structure? Then, like, there are different approaches, like
Yeah,
mechanical.
there are different approaches, and you cannot tell that this approach is best and that approach is bad. You
No,
have to this has to be considered on the type of materials and what type of structure you want to do.
okay.
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 Uh, Suppose I am telling you here, this severe plastic deformation. This is one method in the top-down approach. The material, what you can do it here, that cannot be done by the rapid solidification technique.
Okay.
Okay,
Yes, sir.
because one thing is some of this material melting point is too high that you cannot utilize it here.
Yes.
So depending on the material and different methodology has been developed depending on the type of materials it is. Okay. There are some materials which is good by good ball milling, particularly I am talking something with the ceramic materials that cannot be done with the severe plastic deformation or by lithography or by rapid solidification. So a different group has working on type of materials and the type of processing. Okay. For a definite type of material, a definite type of processing is required. Clear? No?
Yes, yes, sir.
So just to have a better idea that top-down process and the bottom-up process. This is the start of the bulk wafer. Both the cases we start with the bulk wafer, then apply a photoresist for the semiconducting applications. You use the UV exposure and go through the mask and etch the wafer with desired patterns. This is a top-down approach. In the same thing we can do in the bottom-up approach. We can select after area of a structure is to be created by adding polymer or seed crystal on either technique. We can put some seed crystal and we can grow that crystals on the top of it. So this can give a picture how the similar type of materials, how the top-down approach and the bottom-up approach works. There is another way, top-down approach and the bottom-up approach. Each approach has an advantage and a disadvantage. What is the advantage of the top-down approach? It can be produced in a large quantity. Particularly for most of the structural application, you require a large quantity of materials. So that's why the top-down approach is good for the structural materials. Large scale production, deposition over a large substrate is possible. And in this case, chemical purification is not required. What is the advantage of the bottom-up approach? You can go for much finer nanoparticles, nanocells, nanotubes can be prepared through the bottom-up approach. Deposition parameters can be controlled very well. Narrow size distribution is possible. And another big advantage of the bottom-up approach is the cheaper technique. It is not a very costly technique. What is the disadvantage? Major disadvantage of the top-down approach is the broad size distributions of the nanoparticles. Unlike the bottom-up approach, you can control very narrow size distribution, but here the broad size distribution 10 to 100 nanometers or more. Varied particles shape and geometry. Shape also changes. Control over deposition parameter is difficult to achieve, but in the case of the bottom-up approach, it is can make a better control on the parameters. In this case, impurities is mostly the stress, defects, imperfection that is play a major role, but plays a major role. But here, another problem is that it is a very expensive method. Unlike the bottom-up approach, it is a cheaper method. This is the expensive method. What is the disadvantage? Large-scale production is difficult. Chemical purification of nanoparticles is required. That is one of the major disadvantage of the these two are the major disadvantage. That is the large scale production is not that easy like this top down approach, and chemical purification is required, but in this case there is no need of chemical purifications. So these are the advantage and the disadvantage of the nano materials prepared by top-down approach and the bottom-up approach. We will end today here, and next day we'll go for the material preparation and their application. Any question?
Yeah, there is a question Ronak asked in the chat box. So why it is easy to control the parameters in bottom-up approach?
Yes, here the chemical reaction is taking place, and if we put the pH value, if we put the temperature, then we can really control the chemical reactions. But bottom-up approach, but in top-down approach, it is a large-scale preparation, so control over the large area is very difficult. That is one of the major reasons the control is poor in the case of top-down approach.
Oh, okay, sir. Thank you. Thank you.
How do we do that?
Can you tell one? I cannot hear you properly. Can you repeat your question? Devasis, no? Can you repeat your question once again?
So you can see in the chat box, sir. So what is chemical purification?
Chemical purification. Chemical purification means, you see, after preparation, the material may be acidic or the basic in nature, but you cannot use that in applications. So you have to purify and make it is a neutral for application point of view. And not only that, there may be lot of other chemicals also present in that in your product. So you have to get rid of those. Suppose you want to make a copper nanoparticles. Okay. So with the copper nanoparticles, there are other chemical also be prepared. So you have to take it out from that, and that purification is very much necessary. But in this case, suppose you want to make a you have a iron copper alloy, and you want to make a copper nanoparticles within this iron. What you can do? You can do some treatment so that the copper is precipitated over this iron. So there is no question of purification. But yes, problem is that the copper size will not be uniform throughout this material. Clear, Devasis? Any other question?